Okay. So let's get started. So there's a review session. I sort of sent a late reminder this morning, but it's not late. It's still happening. So yeah, so this evening SAS has one, and then I'll have one tomorrow at the same time I had it last time, 5:30 to 6:30. I will record it. So it takes a minute it seems that in the evening, for some reason, Zoom takes longer to process the videos. So it took, I think, almost a half hour, an hour for it to sort of process. And so I try to get it up as soon as I can. So if you can't come to it, it will be up, but you might have to be patient. All right. So great. So today we're going to continue, and remember, material from today and Thursday will not be on this exam, but will be on the exam 3. And we're going to continue today with chapter 4 and talking about applications of differentiable calculus to many variables. And today's lecture will be very, I think, at least in spirit, very familiar to some things you've done in one variable calculus. So let's recall a one variable setup. One variable problem, method, I don't know. So you have some function of one variable, you draw its graph, and of course, one of the things that you're often interested in is finding maxima and minima of the function, right? So you're interested in extremizing this function, in other words, finding out where the maxima and minima occur. And so this picture, we have like 4 possible kinds of values, really, when we look at it. And just to remember, we have 2. So let's say this is an interval AB, okay? And this is the function y, graph of y equaling f of x. So we have sort of 2 interesting things that we learned to find in one variable calculus, 2 critical points, okay? And these critical points we'll label C1 and C2, and they're where our derivative is 0. And these are the points, which means that they're the x values, but then we can look at the y values by applying f, and we'll get the critical values. Okay, so those are the values of f at the critical points. And there's ways of finding out whether these points are local, like learning a little bit about the local behavior of these points. We can use one variable calculus to do that by applying the second derivative test. So that's actually very useful if we're interested in the local behavior of our function, right? We want to find local extrema, but oftentimes we also want to find global extrema. And for that, well, we actually need a result, and we need to know that we have a global extrema. Sometimes you don't. But if you're on a closed interval, we have this theorem, the extreme value theorem, in one variable calc that tells us that indeed we do have a global min and a global max. And so the other 2 interesting points are the endpoints, the values of f at a and b. And in this case, they do give us the global min and max. They're not critical points. Sometimes they're misdefined as critical points, but they're not. So what we learn is that we have a local problem that we are interested in solving, and in one variable calc, and a global problem. And the same is true in higher dimensions. So this book deals with the 2-dimensional case, but there are techniques to deal with any dimension. The tests get a little more complicated and higher than 2, but there's still ways of doing it. Okay, so let's talk about the local solution, the local method. So local method is to find, first step is to find critical points. your function, f. The second step is to apply second derivative test. And sometimes, this test is not conclusive. So sometimes it doesn't give you the kinds of information you want, but okay. So now so this is the one variable approach. Now let's talk about two variables. So two variables or more. And I'm going to restrict myself today to really just two variables, but I want to mention that there are methods when you go up. So first we need the definition of, because we're going to follow this local method, we're going to follow this method sort of exactly, but we just need the right versions of these notions in 2 dimensions, or maybe 3 if you're thinking of the graph. So we need a definition, which I think I've mentioned before. So a point AB in the domain of a function of fxy is called a critical point if one of 2 things happens. If either f is not differentiable at the point, which is a case you generally don't worry too much about in applications, at least for initially we don't. So not differentiable at AB. Or B, well, or the gradient of f at AB is equal to 0, the 0 vector. Okay, of course, the gradient, you'll recall from last week, is a vector. And if I evaluate at a point, I get a pair of numbers in this case. So both of them have to be 0. All right, so let's do part 1 of our local method for a particular problem. So let's say we have the following problem. Let's find the critical points of the following function. So we'll take f of xy equaling x squared minus 2y cubed plus 6xy. Okay, reasonable question. So for the solution, so we first note, and the problems I'm going to give you, and again, most of the problems you'll see in any kind of application, not any, but most applications, you'll have differentiable functions. So you don't have to usually worry about this lack of differentiability most of the time. But okay, so in this case, you certainly don't, because this is a polynomial in 2 variables. And so this is differentiable and has as many derivatives as you want. So the first thing you do in this case is you take its gradient. You take f's gradient. So we note, we just compute the gradient of f. And recall what that is. I take the partial with respect to x and the partial with respect to y, and I put them in the respective components of the vector. This is a function, these are functions. So I'll get 2x plus 6y here. And then I'll get minus 6y squared plus 6x here. Okay. And now I want to solve the equation that tells me that this equation here, that tells me that I have a critical point. I want to find A and B that are solutions to that equation. So want to solve. It's a vector equation. So that means that both the x component must equal 0 and the y component must equal 0. So we need to solve 2 equations sort of simultaneously. And I'll just write them out. So I'm going to find a pair of numbers, x and y, that satisfy both of these equations. So you might think, okay, well, this is something I learned in linear algebra, if you took linear algebra. If you didn't, you won't think that. But indeed, this is not the case here. This is a harder problem in general, a much harder problem in general. So this is going to be very hard. So most of the problems, you need some estimate here. But in this case, it's not too bad. And the reason it's not a linear algebra problem is because this is not a linear term, right? We have a y squared there. So you have to be a little bit careful. But here it's not too bad. So we can divide this first equation by 2 and see that x equals minus 3y. And here we can divide by 6 and see that y squared equals minus x. But now using the first equation and just putting in minus 3y for x, we get y squared equals 3y, right? Did I do something wrong? I have a minus here. Yeah, thank you. I heard some grumbling there. Good. So this should be a minus 3y, pardon me. Okay, good. So, and now we can continue this and just say, okay, this is y squared plus 3y equals 0, which equals y times y plus 3, which means I have two solutions for y. I have y equaling 0, or I have y equaling -3. Now, you're not done at this point. So there's always this feeling of accomplishment when you get to this point, and you're like, oh yeah, but don't celebrate yet. Finish it up. You have an implication, and sometimes there's other possibilities here, but in this case, y equaling 0 implies that x also equals 0. So here we have x equaling 0, while y equaling -3 implies that x equals 9. So indeed, what we're finding here are critical points on the plane. So we have two coordinates here, 0, 0, and 9, -3 are the critical points. Okay, so most of the problems you'll encounter are not that much more difficult than this as far as finding critical points go. Of course, if you write down an arbitrary function, as I said before, it can be kind of impossible to actually get a closed form solution sometimes. So oftentimes you rely on estimates in practice. Okay. So this is the first part of our method, right? So we have these two steps. The first part in one variable and in two, or really any number of variables, is to find the critical points of your function. The second part is to apply a second derivative test. And I want to just remind you where this comes from, because there's not really a good proof of this in the book, and I'm not going to give you a proof of this, so it might look a little mysterious, but I want to give you at least a sense as to why this works, or where it's coming from. So let me just say a couple of words about the second derivative test in one variable. Okay. And this is the same in many variables as well. The second derivative test is really just a second order polynomial approximation. So what I'm trying to say there is, you'll recall in one variable calc last year, you talked a little bit about Taylor series, hopefully at some point, right? And what Taylor series said is, okay, well, we could write down an equation for a tangent line of a function f at a point C, and we'll get this if we write y equals this. But why stop with a linear approximation? We can keep going. and get a quadratic approximation. And we could keep going, but let's not for today's lecture. So I'll put an approximation here. Now, if C is critical, then this approximation looks more like f of C plus f double prime of C over 2 times x minus C squared. This is this approximation. But you'll notice what this is, right? F of C is a number, and f double prime of C is also a number. And if it's positive, then you get a parabola that looks like this, shifted up or down over C. And if it's negative, you get a parabola that looks like that. And so that tells you that when you look at just the sign of the second derivative in one variable is telling you sort of the shape of the second order approximation and giving you a local min or a local max. Okay? So it's just a reminder. This is where it comes from in one variable. There are similar results in two variables. There is a Taylor's expansion in two variables. But we don't need the full thing. We just need the second order, which is a little more messy. We'll get a z equaling f of xy. But the first part was very familiar. If we're going over a point AB, or in other words, we're approximating the function f near AB, our first part is our linear approximation, which we've already learned last week. And then the second part is a very beautiful expression, and very ugly if you don't write it correctly, as the book does not. So let's write it correctly. What is this second order thing? It's best written as a matrix equation. There's a 1/2 factor in it. And you take your x minus a and y minus b, and you put them into a row matrix. And then you put a 2x2 matrix, which is called the Hessian, but I'll write it out here, I think. It's the matrix of second partials. It's not like the total derivative. It's not the total derivative. It's a different thing. It's a matrix of partials. I'm going to assume everything is twice differentiable, so I don't have to worry about order of differentiation here. Give myself just, well, actually, I don't need it. It's this guy. This will turn into this expression. Okay, as I was saying, this is called the Hessian at AB of f. And if we were to write this out, it looks not quite lovely, as lovely as the matrix equation, depending on your taste. But let's write it out. So we get a mixed partial without the two, because there's two of them. And here we get a product x minus a times y minus b. This would not be fun to write out at all if you were doing it in 3 variables, or it would get more messy than it already is. But at least in 2 variables, it can be written without too much time. So you get this expression. This is the general expression. Okay. So what am I saying? What's the point? This looks a little bit abstract, and we'll do and continue with the example that we looked at a moment ago in a second to apply it. But here's what I want to emphasize to you. If AB is a critical point, then we have the same kind of thing that we had before for one variable. We have the sort of linear parts of x and y here. These guys go away in this approximation. And we end up with an equation that looks like z equals some number plus what I just wrote, this thing, which looks messy, but let's look at it again without feeling too scared. This is a number, so is this, so is this, so is this. Got a lot of numbers there. Just imagine them as numbers. If you were to expand this out, what would it look like? Well, it's a polynomial in the x and the y of order 2. In other words, we're going to get terms like x squared, some number times x, right? Some number times y squared, and some constants, and maybe an xy, maybe a cross term. That's what we're going to get from this thing. This is an equation with z equaling such a polynomial. And we've had occasion to study these. These are called quadrics. In fact, we had this section that kind of classified these types of quadrics, where you had one linear term. So this is a quadric. And there are 3 types here. These are paraboloids. There are 3 types, and I'll just sketch the 3 types that occur. There's this type, there's this type, where you have just 2 paraboloid, a paraboloid kind of going down, paraboloid going up, and then this hyperbolic paraboloid, which is this saddle. And these are the only 3 that are sort of not degenerating into kind of like a parabola across a line or something. These are the only sort of 3 generic ones that you'll see most often. There are exceptional cases that are really reduced down to 1 dimension. So all of a sudden, what I'm trying to say to you is that if we look at the 1 variable case, we had 2 pictures here, depending on the sign of our second derivative. In the 2 variable case, we have 3 pictures, and what it depends on is, in a sense, a sort of sign of the Hessian. It actually really only depends on this guy, this matrix. So any kind of proof that you would ever look at, or any kind of method that you would ever find to sort of reason out why the second derivative test in higher dimensions works, really should be concerned with classifying these quadrics based on this matrix. We're not going to do that here, of course, but I want to mention it to say this is not some weird mystery. This is where it's coming from. So then, without further ado, let's give this second derivative test just to see which one of these 3 possibilities occurs. Okay, so this, of course, is going to be a local max. This is what we call a saddle point. And this is a local min. If you're application minded, if you're like, I hate math, but I really need it to apply to what I'm doing, you should keep in mind, if you have a multivariable situation that you're modeling, right? These kinds of things are really important to understand the structure of. Sure, if you're at a local max, you know that if you move around in your parameter space on the model, you're just going down from that value. But in these, and similarly here, you're just going up. These cases, there's actually some preferred directions that you can identify if you study the Hessian, telling you if you go this direction, you're going to go down. If you go the other direction, you're going to go up. That, of course, is really helpful to know if you're working on a model. All right. So let's suppose that we have f, a function of 2 variables, and that it is continuous, or it has continuous second partials. I'm just going to make it as nice as I can. All right. I'm going to define something they call the discriminant in the book, D. And what it is, although it's not expressed this way in the book, but I'll write out the formula you see in the book, we're going to take D to be the determinant of the Hessian at AB. And what this is, the formula you'll find in the book, is you take F, you take the second partial of F with respect to X, second partial of F with respect to Y, and you subtract the square of the mixed partial. You look, you can see this is precisely this determinant of this matrix here. Take this times this and minus this times this. Okay. This is called the discriminant. Okay. Then if AB is a critical point of F, then F has let's just say one local max at AB. Sometimes you say over AB, but I'll just say at AB. It's a local max at AB if the discriminant at AB is positive, and the second partial of F with respect to X is also a negative part. It's negative. Has a local min at AB if this discriminant is positive, but now the second partial is positive. It's also positive. It'll have a saddle point if this discriminant is negative, and then this is inconclusive if the discriminant is 0. So you can't really say much. I mean, there are some things you can say actually, but beyond the scope of this course. So this test says, okay, look, we can compute this Hessian. Once we compute the Hessian, and I really recommend you do it that way because all the information is contained in there, you can then identify, so long as this D is not 0, you can identify which of these 3 cases you're in. So what the local behavior of your function is near the critical point. Now, you might ask, what about a function of 3 variables? You might not ask, but you might ask, you never know. You see that actually this pattern does continue. When you go up to 3 variables, there become, all of a sudden you have 4 different options. You have an extra option. And on you go. So the more variables you have, the more possible types of critical points you can have. But they're all classified and understood. So it's, worth studying if you are going to use this. Okay, so we've done a lot of kind of formulas and abstractions. Let's go back to our computational problem. So let's talk about this. We took the first step in solving the problem of in solving the local extremizing problem for the function x squared minus 2y cubed plus 6xy. Now let's take the second step. So let's determine the local behavior of same function x squared minus 2y cubed plus 6xy at the 2 critical points we found. So we found 0 at the origin was 1, and 9 minus 3 was the other. All right. So what you'll find on say exam 3, with the problems that I'm asking about these types of techniques, is a problem will usually be broken up into several parts. Now you can use previous work, and I recommend you do because you don't want to have to take extra time to do that. But okay, before we did calculate the gradient, and it was 2x plus 6y and 6y squared plus 6x. And you recall, right, this is f. This is the first partial with respect to x. This is the first partial with respect to y, pardon me. And why am I mentioning that? Because if you want to calculate the Hessian, which you do, if you're going to apply a second derivative, it's good to know the first derivatives. So if you've already computed the gradient, don't do what I just did and recompute it. Just look back up at your formula, and then you can I can take the x derivative, x partial of this to get fxx, and that will be 2. I can take to find the mixed partial, I'll get 6, because this is the y derivative of f of x, of f sub x, I should say. But these things commute, so I'll get 6 here as well. And then the last thing I need to do is calculate the y derivative of this. So this is going to be 12y. So if you're very confused because you sort of zoned out a minute ago to find what the Hessian was, let me recall, this is what the Hessian is. It's these second partials. It's a matrix of second partials. So I'm just filling in the blanks by taking partials of these guys. Good? Okay. Now I need to calculate my discriminant, because to really apply this test, you'll see this discriminant, the sign of the discriminant appears sort of first. So it's best to figure that out. And when we calculated this Hessian, we've already calculated our second partial of x, so we don't have to redo that later. So the discriminant is the determinant of the Hessian, which helps me because I don't have to remember these weird looking formulas. I just remember how to take a determinant of a 2 by 2 matrix. So this is going to be 24y minus 36. Oh, did I do something wrong? I feel like I did something wrong. There should be minus, thank you. You guys got it, be bold and correct me. I'm error prone. Okay, I really appreciate the corrections. I won't get mad. All right, so good. Okay, good. So this should be negative 24y minus 36. All right, so at the origin, what do we get? We get d is equal to minus 36, which when we look back up to our second derivative test, where in this case, d is negative. So this is a set. On the other hand, at 9, negative 3, what do we get? Well, we get that d is equal to negative 24 times 3 is 72, minus 36 is equal to 36, which is positive. Furthermore, as I said a moment ago, the second partial of f with respect to x both times is also 2, and therefore is positive. So we know that we have a local min here. So 9, -3 gives a local min. So this is the way to solve this, define the local behavior of your function at that point. Now, I guess this is a pretty big value or something, because I tried to put this into the graphing and it kind of got a little messy, but I did kind of graph it out. This was the graph of that function. So you can see there's some local min that's pretty far off. I guess I could have enlarged it, but you do see the saddle. And so I just want to illustrate that. There is a saddle at the origin. You get kind of a positive direction, and if you turn, you'll see you get a negative direction, depending on where you're going. Okay. So what about the global problem? Oftentimes, you don't really care about what's happening at some random points. You want to say, okay, well, here's where my domain of my function is. What is the largest value of my function, and what's the smallest value of my function? So what about the global problem? Well, again, we can take our cue from, as far as finding a method, from one variable. So the method that we have is first, solve the local problem. In other words, find your local extrema. And the second bit is look at the boundary and solve and extremize, I'll say, and extremize in one less dimension. And I'll explain what I mean by that. Dimension -1. This is a general thing you can do. So this is not something that you just need to do in 2 variables. Point is that if we look way back up at our original setup, what is the method that we extremize on the entire closed interval? We find our critical values. We find their values, f of a, f of c1, f of c2, but then we need to go to the boundary and we need to evaluate our function there as well. If we don't do that, we won't get a global extrema, generally. So this is the same method in higher dimensions, except of course in higher dimensions, our boundaries get more interesting, more complicated. Now, before we go ahead and apply this method, it's very useful to know that we do indeed have a solution to this problem. And so there is an extreme value theorem in arbitrary dimension, but we have to phrase it correctly. Let me just say it is. It just says that if f is a continuous function, doesn't have to be differentiable, on a closed and bounded domain. Remember, we defined these terms a few lectures ago. Closed and bounded domain. Inside of n-dimensional space, doesn't matter what dimension, then f attains. In other words, it's not like there's some upper bound to f. It actually will reach that upper bound, a global minimum and maximum. Okay. So this is an important theorem because, it's really disappointing to try to solve a problem that doesn't have a solution. I mean, of course, if you're on an open interval, for example, right, you don't have your endpoints and you look at your function, say a function like that, there's no global max or global min, because you would like to say it's this value, but since you're on an open interval, it never reaches that value. So there's no actual global maximum attained. And if you're not bounded, you have pictures like this that will never, reach a maximum, or that could just go up forever. So if you're on a closed and bounded domain, you're in good shape. And we can actually pursue this method. However, in higher dimensions, this part 2 becomes slightly trickier. Because in dimension 1, 1 minus 1 is 0. So if we want to extremize on a 0-dimensional space, we just put those points into our function and we see how big they are. But in dimensions 2, we have some domain. Maybe it's closed and bounded. We have a function defined on it. And what we do is we find some critical points. We can find critical points. We'll see if they're maxes and min, or just take their value so we can compare them with the boundary. But now we have to look at the boundary. And the boundary is now 1-dimensional. So how do we extremize on this 1-dimensional curve inside of 2 dimensions? Well, we parametrize the curve. That's the first way we can do this. So we find a parametrization, R, T, sending us to the boundary. And then we extremize F composed with R of T. That's a 1-variable function now on a closed interval because this is bounded. And then you do the 1-variable calculus problem and you solve it. Then you compare those maxima and minima with the maxima and minima you got on the interior, and then you're done. Should we do an example? Let's do an example. There is another, was there a question? There is another method, which we'll do next time, of Lagrange multipliers. But right now, this is the method we'll look at. Okay, so let's find a global max. Say the global max. Question? It's okay. And global min of, let's say, f of xy equaling x squared minus x plus y squared on the disk, closed disk, x squared plus y squared is less than or equal to 4. So what we're going to do is pursue this method. So first we'll solve the local problem, which means we need to find critical points. Sometimes there are no critical points on the domain you're considering. Then you just move on to the second part. But let's take a look. Let's calculate the gradient of f. It's going to be 2x minus 1, 2y. So now if I want to set this equal to 0, so delta f equaling 0 gives 2x minus 1 equals 0 and y equals 0. And in this case, we have a very easy solution. We have x equaling 1/2. And we have y equaling 0. So, and now, okay, so the only critical point is 1/2, 0. It's the only critical point. And it's important in actual problems to make sure that your point is indeed in your domain. Right, this is the domain we're considering. This is where we're trying to extremize. And indeed, okay, this does satisfy that inequality, so we're okay here. Now, you could quite easily get the local behavior of this point. Let's do it just for fun, but it's not necessary to this particular problem. So local behavior, we find the Hessian at this point. Well, Hessian in general really is the same at this point, it's constant. We'll get a 2, 0, and a 0. And so, well, the discriminant here is equal to 4, which is greater than 0, and fxx is equal to 2, which is also greater than 0. So we get a local min at this point. F has a local min. Now, there's a subtlety to the language here, and it confuses people for a long time, even people that work with this stuff. People will use the wrong language, often mistakenly. This is a critical point. If I want the critical value, I put it into F. I just put this point into F. So this F has a local min at this point, but the value of F, critical value, so the local minimum value is just F at this F of 1/2, 0. Okay, so well, in this case, going back up, we get 1/4 minus 1/2, so that's negative 1/4, plus 0, so that's negative 1/4. Okay. Now, what do we do now? So we have this disk. Whoa, I don't know why it's blue. It is. We have a critical point somewhere in that disk at 1/2, 0. Now we need to actually look along the boundary. And in this case, we can parametrize it because the boundary is a circle of radius 2. So let's parametrize that boundary. So parametrizing gives r of theta, I'll call it theta, equaling 2 cosine theta, 2 sine theta. And now here, theta is also on a closed interval from 0 to 2 pi. Now, so that gives me a way of giving me a one variable path, along this boundary. And I want to stick those points into F. And that will give me a graph of a one variable function. And then I want to check and extremize that function. F of r of theta, this is F of 2 cosine theta, 2 sine theta, which, looking back up at F, we get an x squared plus a y squared. And if I square these guys and add them up together, I get 4. So that gives me 4 minus 2 cosine theta. Just the cosine squared plus sine squared turns to 1. So now, as I said, I want to extremize this function on this interval. Well, that's not hard. I can just take the critical values or critical points. So d theta of f of r of theta. This is just equal to 2 times sine theta. And I want to set this equal to 0. But this is only 0 when the, theta equals 0 pi or 2 pi. Now, in fact, 0 and, as I said, these aren't critical points at 0 and 2 pi because they're endpoints. They're sort of both in this case. But all right, we need to, if we're going to extremize, we need to check the endpoints anyway. So if we check the endpoints, we'll see that f and r of 0, this is going to equal f of r of pi because they're indeed the same point. R of 2 pi is the same point as r of 0. And this is going to be equal to 4 minus 2 times cosine of 0, which is 4 minus 2, or 2. Meanwhile, f of r of pi, this is going to be 4 minus 2 cosine of pi. Cosine of pi is -1, which is 4 plus 2, 6. And now I have what I have in one dimension. Think of what you do in one dimension. You put in the critical points, you get the values there, and then you put in the endpoints, and you get the values there, and you compare them all and find the biggest one and the smallest one. We've got 3 of them. The largest is 6, and the smallest is -1/4. So this is your min, this is your max. Okay, guys. I will hopefully see you tomorrow at the review. Please send any questions you have as soon as you can.